Let's now take a look at an example. So in this example, we have a charged particle which is moving with a uniform velocity of 4 meters per second in our x direction. And in this region where it's moving, we have an electric field of 20 volts per meter in our y direction and a magnetic field of B naught Webers per square meter in the z direction. And so what we're wanting to find is what is the value of this B naught such that our particle velocity remains constant. So we want it to remain constant at that 4 meters per second in the x direction. Or in other words, we want it to be our magnetic field strength B naught to be a value such that our particle is not being deflected. And so we'll see that here more clearly in a little bit. So as always, a good first step is to draw out what this system looks like. So here I have our rough system. So we have some coordinate system here. Notice we have x going left to right, so we have our charged particle moving towards the right with velocity u, and of course that is sort of just a stand-in for our 4 meters per second. We have our electric field represented by these two blue lines, and we notice that is in our y direction, so that's in our y direction here. And so I've kind of got these between two plates. So of course, in practice, if we're going to have an electric field, it's going to be between two plates. So maybe we have some voltage or potential difference applied across plates like such. And then finally, we've got our magnetic field represented by these red circles. And the dot in the middle of the circle indicates that's coming out at us, as is our z direction. Okay, and so we notice that our electric field, our magnetic field, and our particle velocity are all mutually perpendicular, which is an important thing to note. So as this charged particle is moving through this electric field, this magnetic field, it's going to be experiencing or potentially experiencing two forces. So we're going to have one force due to our electric field, and so that's going to be a value of QE. And so I'm just using a general value of Q right now. We've not specified whether this is a positive charge, a negative charge, or the magnitude of the charge, but we'll touch on that in a little bit. And we also have some magnetic force that it's going to experience in this region. And so as we talked about, our magnetic force is equal to Q times the velocity of that charge crossed with the magnetic field intensity. And so let's for a minute say that this is a positive charge. So let's say we have a positive charge Q plus, and if that charge is positive, then that means our force from the electric field is going to be pointed in the upward direction because we have a positive Q and our E is in the y direction, so our force is also going to be in the y direction. Our Fm, on the other hand, we need to do a positive Q times U, so that whole quantity here is going to be in our x direction. So we could say our direction is going to be U of x cross with our B, which is in the U of z direction. And so we can use our right hand rule. We put our fingers in the direction of x, curl them towards towards z, and we see that our thumb is going to be in the negative y direction. So we have negative U of y, and so the way we have our axes set up here, that's going to be downward in this case. So what we see is we have opposing forces. So our Fe is pushing upward or pulling upward, depending on how you want to look at it, and our Fm is pushing or pulling downward on this charged particle. But in the problem statement, what we're looking for is we're looking for a value of this B naught such that that particle velocity is remaining constant. And so there's sort of two ways that we can look at this. So the first is we can say we want a constant velocity of 4 meters per second. And so of course, if we have a constant velocity, that means we have zero acceleration. And so if we have zero acceleration, then that means we have zero net force. And so that comes from Newton's second law. So from Newton's second law, and of course what Newton's second law says is that in general our force is equal to the mass times acceleration. And if our acceleration is zero, then we have zero force. So because we have one force pointing upward and one force pointing downward, that means we want these forces to exactly cancel out. So we can say that zero is equal to our overall force, which is going to be equal to the sum of the two forces, which is our Lorentz force equation. So we have Q times our electric field plus the velocity of our particle cross with our magnetic field B. And so right away what we can see is that Q is going to cancel out because we can divide both sides by Q and that's going to go away. And so ultimately what that means is this is going to be independent of the charge. So if we had considered a negative charge, for instance, we would have seen that our electric field force would be pointing downwards and our magnetic field force would be pointing upwards. So same basic idea, we just sort of switched the directions around. Okay, so let's plug in our actual values. So again, that Q doesn't matter, but we have a direction and magnitude for our E. So that was 20 in our Y direction. We have our desired constant velocity in our X direction. So that was 4 meters per second in our X direction, and we're crossing that with B naught in our Z direction. All right, and so what we can do is we can move our 20 u of y to the other side of the equation, so we have negative 20 u of y. And so when we do this cross product, as we said, that unit vector ux cross uy is going to be negative u of y. And then we're going to have the two magnitudes multiplied together, so we're just going to have 4 times b naught. And so of course the negative u of y direction is going to cancel out, and ultimately what we see is that we need a b naught of 5. So we need a magnetic field strength of 5 Webers per meter squared in order for this particle to maintain a constant velocity as it moves through this region with B and E. And so, as I mentioned in the problem statement, an alternate way to say that is we've adjusted this B naught such that our particle is not being deflected. So what does that mean exactly? So let me move this around a little bit and let me add something to our figure here. So let's say maybe we had some aperture on the other side. So basically we have some slit or some hole through which our particles can pass. And so if our particles, and let me line that up with where our particle is incoming there. And so what we're saying is that if our particle is able to maintain that constant velocity and it's not going to be deflected at all, it's going to be able to go straight through that aperture. However, if the particle velocity does not meet that requirement, then it's going to be deflected as it's moving through here, and it's going to be stopped. So it's going to be running into some part of this blocking mechanism. It's not going through this aperture right here. So let me go ahead and label that actually. So this is our aperture. And so ultimately what we have here then is a velocity filter. So it's able to select particles based on what their speed is. So we have a velocity filter. And so what we've done is we've sort of designed this for a certain velocity, but of course we could go the other way and we could adjust our B and our E in order to filter for a desired velocity. And so as we kind of touched on earlier, this is going to work regardless of our charge and regardless of our mass. So this works regardless of the charge and the mass of that incoming particle. And so this has a lot of interesting applications whenever you're dealing with ion beams. And so one thing we can relate that back to, of course, is ion implantation when we're dealing with semiconductor materials. But that's just sort of the tip of the iceberg. Of course, there's a whole subset of physics devoted to ion beams and a lot of interesting applications. So let's say we wanted to use this sort of how I mentioned in the second sense. Instead of designing for a particular B naught, let's say we want to adjust B naught and E to get a particular velocity. So in that case, what we can do is we can equate our FM and FE magnitudes. So let's say we equate FM and FE. So those are the magnitudes of our forces. And because our Fm is QU cross B, remember that's going to be QUB sine of theta, but if we're just looking at the magnitude of that, that's going to be QUB. And then for our electric field force, or our electric force, we're going to have QE. And so again, we see our charge is going to be canceling out. And so we can see if we want to filter for a desired velocity, that's going to be equal to our electric field strength divided by our magnetic field. And so, of course, the sort of thing we have to keep in mind though is we have to apply these in a certain manner. So we have to have our electric field, our velocity of the particle, and our magnetic field all mutually perpendicular to one another.